Hello, everyone. We are the snowmelt-timing team, and then we would like to thank everyone for sitting and then for the team leaders, and then also for the organizers. And so we would like to remind you how the snowmelt timing is super duper important because it is vital to manage the water resource, and about the 1/6 of the world population is depending on the snowmelt stream flow. And it is also important to control the environmental events, the critical events such as the wildfire and drought. And also it is also the snowmelt timing is important to predict and also model the albedo, which is a critical factor for the climate change modeling. And for the from the SnowEx perspective, the in-situ measurements are also the really super duper important because it is the really real document of the snow hydrology, including the seasonal snow evolution over the period. And also it is the data, the ground data is important to quantify the uncertainty in the remote sensing or airborne based estimates. So we would like to present one previous study. So this group published this paper really this year, like February something, and then they have applied the MODIS snow cover product, and then they suggest that 7% of the Western United States show the significant trends of earlier snowmelt, and then 2.6% of the Western United States have the delayed snowmelt timing. But the thing is that there is a limitation in their result because they have only applied the MODIS, which means that they have little considered the uncertainty related uncertainty in the estimates related with the timing, related with the spatial resolution of MODIS. So from that perspective, so initially, as you may remember, I pitched this idea for this 1 week that we are gonna estimate the uncertainty in the snowmelt timing from the MODIS product, and then we could also analyze the long-term trend, and then how those long-term trend of snowmelt timing could be related to the meteorological or topographic effects. But it turned out we have some kind of difficulty that we are gonna talk about. So we have switched our goal a little bit, and then our new goal is to present the overall seasonal profile, how the snow is packing and the ripening, and then eventually run off and then melt. So that's our new goal. And then for this whole week, is always the the goal of this hack is to get to know the community and then to know this new data and the new tools. And then a lot of us are really beginner of the Python and GitHub and Jupyter Hub. So we were always struggling, like how to push, how to pull, how to push, how to pull, like something like that. Anyway, yeah, Megan was big help. Yeah, it was fun. Okay, so here, okay, so she's gonna present the study site.
No, it's okay. Okay, so this is our study region at Grand Mesa, Colorado. And basically there are 6 SnowEx pits. And then those sites conducted weekly measurements during the 2020 time series campaign. And then they're grouped by open and treed pairs. And those pairs are 200 meters apart. And then the initial pits were dug in December. And then weekly measurements took place in January through the onset of COVID. So like mid-March. And then one person remained and then began to take more measurements through April and early May. And then also in most cases dug a morning and an afternoon snow pit. And then the SnowTel data that we used was from Mesa Lakes, which is 1.6 kilometers away from the closest SnowEx site, which is Skyway, and it's in green, or like the SnowTel is in green. And then Yeah, so snow pit profiles were taken from snow depth and the density. And then we derived the suite from that. And then we use that as our project like metric.
Okay, I'm just going to talk about the data remote sensing side of things. We decided to use MODIS as our team. Like I said before, it was one of the platform that was used in one of the papers we reviewed. We went on to use Sentinel-1, Sentinel-2, and partly Landsat for the image compilation. We've written here why we decided to use those satellite platforms in that they meet different criteria, different temporal resolution, different spatial resolution and spectral resolution. They both have different high radiometric sensitivity. And we've also listed the pros and cons of them. And these pros and cons are what we use to merge the advantage of one over the other. And then the whole process continues. We expected Megan to come and explain to us SnowEx. Okay, it is just an image of how data were collected. Okay, here is the project flow, and we thought project flow should be needed for our team to give us a coherent way of working, to promote collaboration, which is the basic foundation of Quick itself, and to also have a project management process. So you can see diagrammatically, we have the data site, then we have where we collected the data from, we have the platforms we used and how that link up with Python, Google Engine, GitHub, Jupyter Lab, and the outcome of that. And then it gives us the project delivery itself in terms of snow melt time series analysis. And we divided that into the snowpack moistening, the ripening, and the runoff, which is what our aim and objective of the project is from the beginning.
Hi, I'm Mahuba. We actually work together a lot, but because of time limitation, I just want to talk very generally. Yeah. Catherine and I worked on MODIS estimation by using Google Earth Engine, and we got fractional snow cover in order to compare to SnowEx observations. And here the bold line is the end of a snowmelt, and the dashed line, which is derived from Google Earth Engine, is the first, actually a snowmelt onset. So here is some numbers which shows a snowmelt timing using MODIS, which is derived from another Google Earth Engine code. And I think Catherine can talk more about it.
Oh, sure. Yeah, so you're interested in when snow, like if you just optically, when you would notice snow cover disappearing. And so this script in Google Earth Engine finds the first day that the NDSI goes to 0. And that's what marks the MODIS snow cover. But then we're using that to then compare to these other remote sensing sources that people are talking about and bringing up.
And then for me, I ended up, Eric and Santiago had worked on Sentinel-2 and Sentinel-1. For me, I had worked on an NDSI for the frames that these spanned from as early as January 15th, going until about July near the end of August. As you can see with the red, that indicates heavy snow cover. And then as we go on time, so that was it for the NDSI part of it, or normalized difference snow index. And then here goes for the NDVI, and going for that as well. And then here for the next part, I ended up using a script from StackStack to create a compilation of imagery from Landsat 8. The reason I had to use Landsat 8 for this part was because when using the Sentinel part, the Sentinel GIFs were over 150 megabytes. So this project or this slide would have had issue loading. And then there was also multiple crashes. So I'll troubleshoot that later. But these are essentially, as you see, top half is starting in 2019 and then ending at that point. And the below is the NDSI part for that compilation or the GIF. For the limitations that we experienced at Grand Mesa was in 2 UTM zones or EPSG points, because as we know with Sentinel-2, when making the code and when Eric made the code in Python, that there was an issue with attempting to trying to get it to work and then troubleshooted it, fixed it. But yeah, aside from that, there was also conflicts between obviously different bands between Landsat and Sentinel. So then that was the issue trying to make this. And then also noticing when we're making this that each GeoJSON had an issue where some of it had worked on April 1st or started April 1st, and then some started in March. So that was a limitation that arose as well. And then from those 15 that presented earlier, from here, I making the mean values of those 15 frames that were collected.
Okay, so this ended up being a pretty rudimentary part of this project. So here we're just showing the distribution of NDSI values in histograms over the time series. So we can see that we have a really big spike in high NDSI values in the months of April and early May. But one of the limitations with this is that the temporal resolution doesn't really tell us when we're really seeing the big jump from high to low NDSI values. And then on the right, I was just curious about if by calculated NDWI, if we would be able to see some sort of patterns that would go along with the big decrease in snow from early to May, but we don't really see any changes in NDWI values throughout this time series. So some of those limitations of this part of the project was the temporal resolution, and then because Sentinel-2 is an optical sensor, we can't really, evaluate any liquid water content, which we already knew. But perhaps most importantly were my Python limitations, because there were some other ideas that didn't really come to fruition. But something that we would have liked to present was like the NDSI value for the specific snow bits and compare that to the SnowEx data. But yeah, we'll get it next time.
Hey y'all, I'm Eric. So I worked on Sentinel-1. I got to try out some tools that I've been building for my research for time series analysis of snowmelt using SAR. And so in the top left here, you kind of see some time series of some SAR images from the time period that we analyzed from, which is December 2019 to August 1st. Of 2020. So what you're seeing, the backscatter can tell us some interesting things. One, when you see a big decrease, the strongest negative gradient in backscatter, that's usually when the snowmelt is ripening. And then at the backscatter minima is when the snow has become super saturated and starts to flow out. That's usually when what we call the runoff onset date. So in the top right here, you can see a map of Grand Mesa, and the different pixel colors correspond to the day of year that we estimate that snowmelt runoff onset happens. And you can kind of see areas where it's pretty coherent, and then areas where you could guess that there's vegetation, because in these vegetated areas, the snowmelt timing control on the backscatter isn't as strong as, interaction with vegetation and such, since we're using C-band radar. And then in the bottom right, you can see backscatter along with NDSI and some other snowtail metrics here, like precipitation. So the blue bars are precipitation bars and the pink bars are snow bars. So that helps us understand like what might be like a rain on snow event, and know when snow is accumulating, and we expect a jump in backscatter then. And so we zoom in a little bit to where these SnowEx pit sites that we have. They're a little bit hard to see on here on the top plot, but if you look on the far left plot, those are the 6 different sites. So we have the 3 different sites, and each one has the tree and the not tree. It's probably a word for that, but so you can see the day year estimates around this with a 100-meter buffer in all directions. And as you can see in the right-hand plots with the actual backscatter, you can see where there's big drops, especially on the left plots, because those are the open areas. The right areas are the trees, so you're not going to get as clear of a signal. So if you look just at these 3 left-hand plots, you see that big decrease. So that's when the ripening is happening, and that minima is happening whenever you have the runoff onset.
It's so small. Yeah, so I think it was pretty quickly clear that the optical sensors that we were working with have some limitations when looking at the process of snow melt. Given that we're trying to kind of calculate the process of snow melt by looking at when snow goes to 0, which isn't super useful for our purposes. So yeah, we put all of this information together, and like Eric was saying, in open areas, these 3 different data sets kind of align pretty well. So you can see the snowpack moistening and then ripening at that kind of decline in the Sentinel-1 backscatter. And then runoff onset is kind of where you can see the MODIS pixels, fractional snow covered area kind of reducing. And then this is what it looks like in the trees. So I think for me, it was really interesting in this project to like just basically highlight the uncertainties that come from using optical sensors for understanding a process that really should be looked at with something more like Sentinel-1. And there was also some limitations with our different study sites being close together, and using MODIS is maybe too coarse for our purposes as well. And I think, oh yeah, you?
So we also performed a quick empirical modeling using the SnowEx data to estimate the 2 important timing. One is the melt in timing when the snow runoff starts, and then melt out timing when the snow runoffs end. So we fitted this double logistic curve to the SnowEx suite in 2020, and then we defined the snow melt in timing as when the curve hits the maximum. And then we also defined the snow melt out timing when the curve hits the 0 point. And then we also added these 2 data points. And then it is the first figure from this county line open. It highlights the importance of the data for during the snow melting season, because obviously the logistic has no data points to get fitted. And then you can see that for those 2 sites, Skyway tree site and the Skyway open site, and then you can see this melt in and the melt out timings defined from the function. And then you can also see that the melt out timing at the Skyway tree is also really close to the Snowtail Mesa Lake site, which has tons of data points. And then, which is also 1.6 kilometers away from this Skyway tree site. And this may be because you can see the snow depth profile from these 2 sites, that maybe the feeding works, the method of feeding curve, logistic curve works, because given the snow depth at these 2 tree site and then snowtail sites are closer than the open site and then the snowtail sites. So the result from this study, this quick test may suggest that the fitting a logistic curve to the data points would be a useful way to define the timings when there is only limited number of data points. Still, we need something. So that's about it from our results. And then, of course, we had many challenges. First, we had some trouble to find the suitable snow pit data for our initial goal to uncertainty analysis. And so we switched the gear. And then we also struggle with the UTM and the projection thing. And then, of course, there are always problems with we also struggle always due to the missing data from the nature. So our future work, would be would be to complete this analysis of the snow evolution, and then maybe we could add more satellite data and more analysis as always. Thank you.
One reason you had trouble finding kids during the melt period is the Grand Mesa IOP was designed around trying not to see melt because it screwed up the microwave sensors.
Oh.
Sweet. So, awesome project. I think there's a lot of tie-in to the modeling group, which we'll hear from in a little bit. There was some measurements that were made through that melt period by the student. Megan, are you going to speak to that? Oh, these are the time systems. Which did go partway into melt, but we did end more significant melt just again because of the remote sensing strategy.
Real melt cycle, it does align pretty well with like MODIS fractional snow covered area kind of reducing or I guess at that point, like getting to the, yeah.
These are exciting results. It's neat to see all these different tools. Transition from dry to melt to start happening more and more. Nice job.
Okay.
I think we have cold fusion up next.